Hey everybody, Mr. Troy here. I got the flame of knowledge burning. I got an ice cold LaCroix. Let's do this. It's time for math with Mr. Troy. All right, everybody, we're going to finish up with our applications of logarithmic functions and exponential functions, and then we are going to be done with logarithms and exponential functions. We'll do a little bit of review just to make sure you feel like you know what's going on, and then we will move on. We're going to start by looking at Gaussian models. A Gaussian model is one that's used in probability and statistics to represent populations that are normally distributed. We're often going to just use Desmos to estimate averages for things like this. It's going to be some number times e to then this fraction, the opposite of x minus b squared over c. So an example here. In 2013, the SAT math scores for college-bound seniors roughly followed the normal distribution where x is the SAT score for math. Using a graphing utility to graph this function, estimate the average SAT math score. If I graph this, what I see is that bell-shaped curve that I'm used to. Your stats teacher will spend a lot of time talking about the difference between the word normal and the word bell. But for our purposes, what you need to consider is that this means that scores in the center are more likely, whereas scores towards the outside, either scoring a perfect 800 or let's say an imperfect 200, those scores are less likely. This appears to be centered around 514. There's actually quite a simple reason for that. And the simple reason for that is that our original function, the original Gaussian model, was centered at 0. If we go back to our equation, this is taking that function and shifting it 514 units to the right. So that would be centered at 514. That's all this question is asking you. Where is the average? Next example. So we're going to look at the logistic growth model. As we saw in our video before spring break, some populations initially have rapid growth followed by a declining rate of growth, as indicated by the graph. When you're in biology class, you'll either talk about this having to do with bacteria cultures or carrying capacity, like the deer on an island problem, if you've ever read about that in your biology class. This curve is called a sigmoidal curve. That's just when something grows nearly exponentially at first and then basically flips and mirrors. Remember, that point in the middle is called the point of inflection. Our next example has to do with the spread of a virus. Sorry if that hits too close to home. Here we're given that c over 1 plus a is the initial value. That's because x equals time. And if we plug in a time of 0, e to the negative bx is going to be e to the 0, which is 1, thereby turning the denominator into 1 plus a. So c over 1 plus a is the initial value. C is the carrying capacity, or the limiting value. What is the largest number of something that could happen? And B is a constant that has to be determined by the rate of growth. So I'm going to let you read this problem. I'm not going to read it to you. So pause the video and read this. We need to work a little bit to figure out what our a value is. Since c over 1 plus a is our initial value, and we're given that that's 1, that tells us that a has to be 999. C, the carrying capacity, was 1,000, so we have 1,000 over 1 plus a equals 1. Therefore, a must be 999. They've asked us what is going to happen after 10 days. So first we need to write the function. After we write the function, we need to plug in 10. If you plug that into your calculator, you get about 293.8. So we're going to round that up and we're going to say 294 people. Another thing that uses a logarithmic model is the Richter scale. The Richter scale measurement gives you a measurement of the intensity of the waves of the earthquake compared to the minimum intensity of 1 that you can use for comparison. In 2014, Edgefield, South Carolina experienced an earthquake that measured 4.1 on the Richter scale. In the same year, Nago, Japan experienced an earthquake that measured 6.5. Find the intensity of each earthquake. So we're going to plug this in. When we plug in, we have 4.1 equals the common log of I over 1, and 6.5 equals the common log of I over 1. To solve for South Carolina, we're going to raise 10 to the 4.1 power, and for Nago, Japan, we are going to raise 10 to the 6.5 power. When we do that, we get a number of 12,589 for South Carolina and about 3,162,278 for Japan. When it asks us to compare the two intensities, we're saying compared to South Carolina, how strong was Japan? Or compared to Japan, how strong was South Carolina? We would do that by dividing. The reason for that is we want to know how strong is one compared to the other, as in how many times as massive. If we were to, for example, divide Nago by South Carolina, we would get about 251.2 times as powerful. If you were to take the log of that number, well, don't let me ruin it for you. Take the log of that number. You would get about 2.4, which is the difference between those two numbers on the Richter scale. So the comparative intensity of Nago compared to South Carolina is 10 raised to the 2.4 power, or the difference between the two intensities. All right, here's a question for you guys to do to see if you need some practice, and then we'll talk today in the live stream. All right, thanks for hanging out. I hope you learned something. Do 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 do.